All right, so we're taking a look at homework, shapes of graphs. This is number 5, and we have f of x, at least I have, yours will be similar but different, 12x to the 5th power, which looks like a cubic polynomial, but a little steeper, plus 30x to the 4th. Please play along here, minus 300x cubed, plus 4. And looking at this, I don't see that it is factorable in any easy way. And there's a claim that there are inflection points, which means there's a change in concavity. So I am going to rescale. Let's see, where did my x-axis go? Hello? What just happened there? Oh, I must have accidentally turned it off when I went in here. There we go. All right, so rescaling. Here's my rescale button. I did. I want to see what's going on. And do I want to go much more than that? There we go. So I had to scale to get to see up to around 20,000. And again, I picked GeoGebra because it's easier to scale by just using the Move Graphics tool and picking an axis. Clicking on that axis, you can rescale it easy. Desmos does not yet have that feature, but they will soon. Desmos and GeoGebra are in constant competition to see who can be the coolest graphing tool. So we're going to need the second derivative. So let's find the first derivative. We'll call that, I guess we'll call that d of x like I usually do. And that's going to be 5 times 12, so that's 60, x raised to the 4th. And why am I doing that here? I don't know why I'm doing this here. Plus 4 times 30 is 120, x raised to the 3rd. 3 times 300 would be minus 900 x squared. So that's the second derivative. The third, or no, that's the first derivative. The second derivative, let's call that s for second derivative. And that's 4 times 60. So that would be 240 x raised to the 3rd plus 3 times 120, what would that be, 360? X raised to the 2nd minus 2 times 900 would be 1800x. All right, so there's the third derivative, all 3 derivatives together, aren't they cute? All right, so I think next we need to break out onto some paper. So I think I'll grab a snapshot of these guys for my notebook. All right, so remember this is like number 5 in homework 4.5. And this is the first derivative. And this is the second derivative. And just for fun, remember the other notation we have for that. This would be the derivative with respect to x of our original function. And the second derivative looks like a d squared dx squared of that same function that we started with. So alternate notation I haven't used much lately, but I think I will again soon. We want to know if there's any changes in concavity, which means you have an inflection point. So the second derivative tells us about concavity. And then an inflection point means there's a change in concavity. I mentioned the other day, as a bike rider, I like inflection points because if I am climbing a hill right? Here, the hill is shallow, and then it gets steeper and steeper. And then eventually, though, I'm going to have to crest that hill. So at some point, it's going to stop getting so steep and start getting shallower. And that point where it stops getting so steep and starts getting shallower, that is the inflection point. So as a bike rider, that's important to me because then the slope is getting less and less and less and less till I crest the top and I get to fly downhill. Woohoo. So here we want to find out if there's any changes in concavity. That means we look for changes in sign of the second derivative, so we need to know the zeros. So 240 x cubed plus 360 x squared minus 1800 x equals 0. Let's see, what is the greatest common denominator here? It looks like it's a multiple of 60 is my guess. So I'm going to try factoring 60 out of each. And I'm going to factor an x out. And then we'll see if we need to factor again. So 6 goes into 24 4 times. So 60 goes into 240. Oh no, wait. Yeah, that's right. So that's going to be 4x cubed. 6 goes into 36 6 times. So that would be plus 6x squared. 6 goes into 18 3 times, and there's 2 zeros, so that would be a 30. And, oh, I took an x, didn't I? So that would be a square in the first power. I took the x from the other one. So x squared x, all right. And then it looks like I could have actually factored further. I could have pulled a 2 out also. So I could have factored actually 120x. So then I can divide all those by 2. So that gives me 2x squared plus 3x minus 15. And we could have done prime factorizations on each of those numbers to find the greatest common factor out front, but sometimes it's just as fast to guess and then try again. All right, so then we hope that this thing right here factors, and I would employ factor by grouping to do that one right there. Otherwise, it's guess and check. And actually, I think I can guess at this one. But I'll do factor by grouping next just to double check. So let's see, 2x squared has to be 2x times x. 15 is either 1 times 15 or 3 times 5. And neither of those looks good. Eek. All right, so let's check factor by grouping. Factor by grouping is you have to take 2 times 15. That would be negative 30. And then you look at factors of negative 30. The negative means you have to subtract the factors to get the middle term. So that would be 1 times 30, 2 times 15, 3 times 10, 4 doesn't work, 5 times 6, and none of those give me a 3. So either this isn't factorable or I made an error, or I have to use the quadratic formula. So did I make an error, anybody? Let's see, 5 times 12 is 60, I agree with that. 4 times 6 is 24, so 4 times 60 is 240. That looks okay. 4 times 3 is 12, so that's 120. 3 times 12 is 36, 360, that looks okay. 3 times 3 is 9. 2 times 9 is 18, that looks okay. Plus, 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 minus, minus, minus. 5, 4, 3, 4, 3, 2, 3, 2, 1. That all looks all right. All right, did I factor okay? 6 goes into 24 4 times, right? Yep. 6 goes into 36 6 times. 6 goes into 18 3 times. 60 goes into 1830 times. That looks okay too. And I factored out another 2 here. Cut all those in half. Yeah, looks like I have to use the quadratic formula. So this doesn't factor, but we can still solve. Right now, however, we do know that 120 x equals 0. So x also equals 0. So we got one of them. Now it's just quadratic formula. So x equals the opposite of b plus or minus square root of b squared minus 4ac all over 2a. And here are our a, b, and c. So we have a -3 plus or minus the square root b squared. So that would be 9 minus 4 times 2 times -15. So that changes to a plus there. So always take a little care inside the square root so you don't mess up a sign there. And then all over 2 times 2, which is 4. And what do we get here? 2 times 15 is 30. 30 times 4 is 120 plus 9. Is that right? Yep. So that's the square root of 129. So I have -3 plus or minus the square root of 129 over 4. And I seriously doubt 129 factors. Let's see, 9, 10, 11, 12. Oh, it does. 3 goes into 129. Let's see if we can clean that up. So 3 goes into 129. 3 goes into 12 4 times. 3 goes into 9 3 times. And 43 is prime. So that doesn't really help. So this is not reducible. And let's just double check that those numbers look right for the second derivative. Calculator, please. So I think my fraction is -3 plus the square root of 129 over 4. So I should have a 0 at 2.089-ish. So let's turn off some of these other graphs. Focus on the second derivative. So I should have a 0 right there at 2.08945. Yep, nailed it. All right, so that right there should be an inflection point. Now we really have to double check. So here's how we're going to double check besides just looking at the graph, because you're going to have to show me some work on the test. So here is the work to double check that. New page, original function of x equals 12x to the 5th plus 30x to the 4th minus 300x cubed plus 4. And then we found that the second derivative at double prime of x was equal to what? 240x to the 3rd plus 360x squared minus 1800x. Is that right? Yep. And we think that f double prime of x is equal to 0 if x is equal to 0, or -3 minus the square root of 129 all over 4, or -3 plus the square root of 129 all over 4. And we know that this one is about, I'm going to call it about 2.1-ish. The other one. -3.6-ish. Right on the graph. Over here, yep, that looks like about -3.6. So then we draw our number line and run our tests just to make sure. So we have 0 over here. Over here would be our -3.6-ish, or let's just call it the actual number. We'll just call it -3.6-ish. And about over here would be our negative or positive 2.1-ish. And that's about, and so we think we might have 3 inflection points, but the only way to know is if you have a change in sign. So then we pick some nice numbers. So numbers to test here might be 1 over here. 3 would be somewhere over here-ish. Over here, I might test -1, and then I might test 4 over there. So I want to know what is f double prime of 4, and the sign is what we need. F double prime of -1, f double prime of 1, and f double prime of 3. All right, back to calculator to make those, and we just need to do it. So I called it S. So S of 4, I think, was one of the numbers. That's a negative. Oops, negative 4. Sorry about that. And it is negative. So that means we are concave down here. And then over here, we are concave up, maybe. Let's check. A negative 1. Positive, yep, concave up. One. That right here. Negative. Concave down. And at 3. We are positive. So we do have changes on concavity. You aren't guaranteed changes in concavity, by the way, at each of these. It could be one of these numbers is not an inflection point. So that was, to make a note, that was positive, and this one's negative, right? Oh, shit. Sorry, shoot, excuse me. I got that backwards, right? Ah, back here. Calculator back. Where'd you go? There you are. Positive for that one, and then 1 was the negative. So this one is negative, concave down, right? This one was positive, that's concave up, and so that's that way. So each of these is a change in concavity. So then to calculate if we need the whole inflection point, we'd have to plug these numbers back in. But we do have 3 inflection points. What did the question ask here? Oh, here. Let's see, D, E, and F from left to right. So we had to get them in order, and then on each of the following intervals, determine the concavity. So our D was our fraction, -3 plus the square root, nope, it's a minus over 4. And then 0 is the next one in order on our number line, and then fraction -3 plus the square root 129 over 4. So those are our numbers, and we did find that each of these did change concavity. And so the first one was back here, concave down, and then it alternated regularly. So down, up, down, up. But you got to check because there's no guarantee. And we got it. Thank you for pointing out my error earlier, Evan. Good job. Glad you guys are noticing. Next one, number 11. X squared times 10 to the x, and the claim is that there's 2 inflection points. And so let's make sure that's true. There you go. So f of x, let's write in red, is x squared times e to the 10x. So we're looking for inflection points. Again, a change in concavity, which means we need f double prime of x. So first derivative here, take the derivative of the first function, 2x times the second, plus leave the first function alone, take the derivative of the second. So derivative of e to the x, or e to the whatever is e to the whatever, and then the derivative of 10x is 10. So I'm going to call that, so I'll just call it e to the 10x times 10. And that cleans up a little bit. I'm not sure if cleaning it up helps us at all. Let's see, we could factor out a 2x e to the 10x. And then that leaves us, we took all of that. I guess that helps a little bit. And then here we would have a 5x left behind. But then we have product of three functions versus product rule, product rule. I think they're about the same difficulty. So we could either use this version, or the other version is, I guess we could just write that as 2x e to the 10x plus 10x squared e. Ooh, I think I see an easier way to write this. We could just factor e to the 10x out, and then we get e to the 10x times 2x plus 10x squared. So we have three different ways we could write it. This is technically the simplest one, but the reason I don't like it so much for the second derivative is we have the product of three functions, so we have to apply the product rule 3 times or twice, which isn't too bad. Yeah, I guess I'm going to go to this one just to practice with you guys of applying the product rule for three functions multiplied. And basically, it's like the 2-1, you just take the derivative as one at a time and leave the others alone, is what ends up happening. We justified that quite a while ago. Yeah, let's do it that way. So f double prime of x. So again, I have three functions, right? I have this one here, I have this one here, and I have that one there. So the product rule for three functions is take the derivative of the first function, derivative of 2x is 2, leave the other ones alone. So 10x, oops, and there, 1 plus 5x. Plus, then we take the derivative of the middle function, leave the other two alone. So I'm going to write 2x. Derivative of e to the 10x is 10 e to the 10x. And then I still have the 1 plus 5x hanging out. And then finally, I leave the first two alone and just take the derivative of the third one. So that would be 2x e to the 10x. And the derivative of 1 plus 5x is just 5. So that right there is the second derivative. And then we try to clean it up. So let's see, what can we factor here? We can factor a 2 out of every term. We can factor an e to the 10x out of every term. So let's start to, and right there, let's start there. And then see what happens next. So let's switch colors for a sec. So I'm pulling out a 2 e to the 10x. So from the first one, that leaves a 1 plus 5x, no need for parentheses anymore. The second one, we left the 10x behind, so I do still need the parentheses. So I have plus 10x, 1 plus 5x. So I got that. And then here, I took the 2 e to the x, so I still have a 5x there. And then we gotta clean this up. So we have to distribute. So that's going to be 10x plus 1050x squared. And we still have the 5x hanging there, and a 5x hanging here, and a 1 hanging here. And then continuing to clean that up, let's put them in order. We have a 50x squared. And now we have 5, 10, and 5 x's. So we have 20 x's. And then we have a 1. Did I do that correctly? That part looks good. That part looks good. Yeah, I think I'm okay. Unless anyone sees anything weird, no chat, so either hopefully we're on the right page here. All right, so then we got to not forget that we have a 2 e to the 10x out front. And I think we're ready to set this equal to 0. Now, e to a power can't be 0. That's not possible. So this breaks up into two possibilities, either 2e to the 10x equals 0, which doesn't happen, or 50x squared plus 20x plus 1 equals 0. And that does not factor, I do not think. Let's see, maybe it does. 50 is 1 times 50, or 2 times 25, 3, 4 times, nope, no 4, 5 times 10, 6, 7, 8, 9, 10. Those are the only factors, right? Because 50 is 2 times 5 times 5. And none of those add up to 20. So we got to use the Pythagorean theorem. I mean, sorry, my other class would do the Pythagorean theorem. In this class, we're going to use the quadratic formula. And everything's positive. Yeah, that looks right. So 50, 20, and 1. So x equals the opposite of b, plus or minus the square root of b squared, 400, minus 4 times a times c. 4 times 50 is 200, right? Yep. All over 2a, which is 100. So that's negative 20 plus or minus 400 minus 200 is 200. All over 100. 200 factors as 2 times 100, and the square root of 100 is 10. So that's negative 20 plus or minus 10 square roots of 2 all over 100, and then we can factor 10 out of the top and the bottom. So if we factor 10 out of here, just want to switch color, we get a 2, 10 out of here is a 1, 10 out of there is a 10. So we get negative 2 plus or minus the square root of 2 over 10 as our two values. And then we would test to make sure on each side of those we change concavity. I'm going to leave that to you guys. So the hard part was taking the second derivative, setting it equal to 0 and solving. And we're going to move on.